Okay, good afternoon. As just mentioned, I'm Andrew McCormick. I'm the Technical Director at Alpha Data, and I'm sort of co-presenting this work that has been largely done by MLE, Missing Link Electronics, and this is adding network protocol acceleration to the CAPI SNAP environment. SNAP, for those who do know, the first three letters are storage, network, and acceleration, and this work has really been focused on making sure we've got that in that acronym. The motivation for this, obviously, all your data has to come from somewhere, so there is certainly increasing requirement for networking within data center systems. There's certainly increasing demand, especially moving towards technologies such as 5G for low latency processing of responses, especially coming from out with your data center, responding quickly to demand. And then there's also a lot of applications, especially moving towards 100 gigabit processing, that basically do not want to put to place all the processing requirements of handling things like TCP/IP stacks within the main CPU, and therefore being able to offload these sort of tasks to the FPGA opens up a lot of applications, and also opens up a lot of acceleration opportunities where you process the data as it's coming in and out of the processing system. And I'm going to hand over to Endric from Missing Link, who's going to go into detail about this implementation.
Yes, thank you, Andrew. So it's been less than a year that we get sucked into OpenPOWER and OpenCAPI. Started at SC17 when we first heard of what I think Bruno called the well-kept secret of the industry, SNAP. Being FPGA programmers, one of the rare breeds of FPGA programmers who accelerate software, that OpenCAPI, CAPI SNAP got quite our attention, and what we're talking about here today is some ideas, some architecture ideas for putting networking, and in particular network acceleration, into SNAP. So the quick background, I just had a longer discussion with a guy from Red Hat. FPGAs are not FPGAs anymore. They're not poor man's gate arrays. They're not even just massively parallel compute beasts. They're fully integrated heterogeneous systems. You can say that on the right-hand side, this is one of the not even most modern FPGAs that Xilinx offers. The Zynq UltraScaler MPSoC. It has a quad ARM. It runs Linux. It has other ARM processors which we're using for security applications, and which can be used for other means like scrubbing and so forth. And yes, there's a lot of programmable logic involved as well. But with these devices, it opens building very heterogeneous, very focused, very optimized systems, and that creates additional challenges. So what we like about this entire approach is that we can build all flavors of accelerators, and that's, Myron, I had to borrow one of your slides. And what we basically see is, without going into details, it allows us to do ingress and egress and actually bidirectional acceleration by hooking up FPGAs. And what we wonder and what we propose here is, why not use 100 gig or faster networking on this side of the equation and put the compute burden where it belongs, mainly in a packet processing system, also called an FPGA, instead of having software, legacy software with legacy stacks running it. One of the reasons that developed over when we kind of sketched out this work was that Power not only has these CAPI connects, but also these PCI Express Gen 4 links. And today, most of the hardware you can buy today is PCI Express based. And what users are apparently looking for is free up those precious PCI Express Gen 4 links and move certain functionality over to those kind of rarely used CAPI links. And what we like about those CAPI links is they're much faster. They're much faster than PCI Express. And when we're talking about acceleration, we not only need tight coupling, but we need sheer bandwidth between the CPU and the FPGA. Now, we all know FPGA programming is difficult. We had a longer session yesterday about Snap, so this is more of a reminder. We're totally sold on the concept of Snap. It was amazing how quickly we got going with Snap, and it was amazing how quickly got first results with Snap. So it was a wonderful investment, and we're more than happy to help turn this into a very well-known secret in this industry. Okay, so what we're presenting today is work based on Snap, where we use the concept of an action for putting certain functionality inside an FPGA, and where we're using the infrastructure from Snap and CAPI to bolt on the network processing part within the FPGA to the network processing part which shall reside on the Power9 system. So let's have a quick look at what network processing really means. And I had to borrow 2 slides from other people. Number one is network processing is about envelopes of envelopes of envelopes, packaging stuff, right? And that's a lot of compute burden, and that's why we have dedicated NIC, network interface cards, with special hardware for processing. On the right-hand side, I just borrowed a slide from Brendan Gregg, who has these flame graphs. It's just one of the applications which indicate, it's more of a stereotype, it indicate the amount of computing that is needed in the Linux kernel today in order to do certain flavors of network processing. Namely, in this case, it's a TCP/IP processing session, right? And what our motivation is to offload the CPUs from this burden and free the CPUs up to do more sensical analytics, for example, rather than just what we would call plumbing. So this is how we see systems today. High-speed networking is connected towards the processor chip. We do scatter-gathered DMA, typically through PCI Express network interface card into the software on the CPU side. And we believe this is not the right approach. Comes with our vision that this side of the equation, on the right-hand side, we see this as an FPGA with accelerator. And Xilinx has networking in their genes. So what we're thinking of basically is putting networking on the right-hand side of such a heterogeneous system and let the FPGA deal with a packet and with ingress and egress, pre-processing or post-processing, and then hand over the payload data to the CPU, to the software side of the thing. And what I'm going to talk through is some architecture ideas that we're having, and quite honestly, this work, the next steps of this work will be heavily steered by the community, by the needs of the applications, because we're platform guys. We need to listen to people who have applications in mind and need to make sure we cater to those applications. The technology underneath, the underlying technology that we're utilizing is a TCP/IP Accelerator Stack that we licensed from Fraunhofer. Fraunhofer started, I guess, in 2010, putting using FPGAs for TCP/IP, UDP/IP network processing. At that point of time, it was a 1 gig implementation. We're now facing a 10, 25 gig implementation. And within the internal data representation, the technology that they basically put together, which is shipping today, is utilizing 128-bit wide data path, bidirectional data path. So given the today's clock speeds of an FPGA in the 300-ish megahertz range, we can easily deal with 25 gig line rates. But in order to meet the next generation of link rates of 100 gig or multiple 100 gig lanes, we know we have to gear up and basically move to what we now consider a 512-bit data bus implementation. The system they put together is basically a very modular system. And if you look at the OSI stack from left to right, you can see that they have the lowest level processing, which is in the physical, the file layer processing, for which we're using the Xilinx PCS PMA layer. And then we have a media access controller, a MAC block, and then there's an Ethernet block, there's an IP block, And these things are connected through those 128-bit wide data buses, streaming data buses, or soon 512-bit wide data buses. And at the end of the day, you have your payload data, and that's where the user logic sits, and that's where the user logic deals with the payload data. Now, when we started taking this Fraunhofer technology under our wing, we thought of this for embedded devices, which have an AXI connect to embedded ARM CPUs. And that's why we basically have this hardware layer, which is the stack control, and an optional DMA. And when we started to look at what CAPI brings to the party, and in particular what Snap brings to the party, we see actually way more potential in using this technology for integrating with software systems than just for embedded systems. So this is kind of the architecture that we anticipate, where we have a software layer running Linux on OpenPOWER in between the OpenCAPI layer. Part of it stretches into the FPGA side with the PSL, the IBM Power Service layer. And within the FPGA, then we have this Fraunhofer stack processing the data from left to right for ingress and right to left back for egress traffic. And eventually, we have the user logic, which talks to the counterpart through CAPI, talks to the counterpart in the software land. And for testing purposes, we use a hardware implementation of a well-known networking tool, which is NetSurf. The Fraunhofer guys implemented in programmable logic most of the functionality of NetPerf, so we can actually run the entire networking sessions for TCP and or UDP within the programmable logic and just have raw data statistics fed to the software. So we can do some testing on how fast we can go and how close to theoretical limits we can drive this technology. So one of the many options which we envision is that we cut up this stack as part of in between the MAC and the Ethernet, and then basically turn some portions become part of what we call the Snap shell, in some flavor open sourced, and the rest of it can become a user or a Snap action, right? That's one of the many ideas we're having. You can go further and do the cut someplace else at the IP layer, so you have ICMP, ARP, and all this kind of management layers of networking also done in hardware. And then basically do the TCP in the user logic. Okay, it's basically the same form of acceleration. What is different here is the licensing schemes, which obviously we have to work out with the Snap people and the Fraunhofer people. And obviously you can go all the way and turn this entire full accelerator for networking traffic into a Snap shell, so users just can bolt on to a streaming AXI bus their user logic in form of a Snap action, like in this particular example, NetSurf. So that's what we've implemented today, and that's what we're running on one of the alpha data cards for testing purposes. So we did the logical cut, which is free of any difficult licensing handling with Fraunhofer, because it just relies on the Xilinx PCS PMA layer, but at the same time it gives you the full user experience of what happens when you offload the entire network traffic and run it within the FPGA fabric. And again, everything is implemented as a Snap action, including the NetPerf, and so you can hook it up, connect it, and drive it. And I guess it runs 25 gig if your cards would run 25 gigs, or if we would finally port it to one of your cards which run for 25 gig, right? But that's basically the current implementation. So here's some results of what we implemented based on Snap. So the first is, that's basically the Linux command prompt from a terminal. And the first step we do is basically start the Snap maintenance tools. And what you can see here is that you see the alpha data card with NVMe enabled and the Ethernet 10 gig PCS PMA layer enabled. all right? And what you also see is we started to work with the SNAP people in Böblingen, and basically took our, honestly, PCI Express ID. We're a member of PCI SIG, so we took our PCI Express ID and turned it into a SNAP ID, and basically are registering here an MLE, HDL, 10 gig Ethernet, TCP, UDP, IP accelerator. What we're doing honestly here is we're not using the SNAP to the fullest extent of high-level synthesis. We didn't implement major portions in C++. We're using the Verilog VHDL, HDL design flow for SNAP for integrating this IP. Then last click, you can basically start the SNAP action, and what you see here is you end up having another network interface device. Under Linux ifconfig, you see npap0 as the network interface device. And in this case, through the maintenance layer, we assign an IP address to it so you can ping and pong and drive it from any other 10 gig connected server. Some first test results, basically showing how fast network processing can be. I didn't bother showing the top for software performance here because no software really is involved on the system. So what you see here is line rates for TCP stream processing is about 9.4 gigs, which is close to the theoretical limit. Okay, that's kind of expected. Good news is we expect the same high rates for 25 gig, close to the theoretical limit of 25 gig. And we believe that we can drive this up and scale to 100 gigs or multiple 100 gigs, knowing how FPGAs process. The bottom part of this slide, we share some round-trip data on the latency. Again, this is FPGA processing involved. It's very predictable latency in here compared to running TCP stack in Linux. All right, and so if you're interested in how this work is going on, we're software guys, so we heavily depend on hardware being available to us. And in driving this current 10 gig implementation, we're working with Alpha Data here to drive this with other Alpha Data cards towards 25 gig and towards multiple 100 gigs.
Okay, thanks, Endric. I'll just talk for a couple of minutes about the cards. These two cards here are the ones that Missing Link have been targeting their framework at, mostly on the KU60, as they've been able to get this into their own lab, but I believe they've also created a port for the KU115 FPGA and ran that remotely. We were also able to take the bit streams they've generated and tested at our own facilities on the KU3 board. These boards are both CAPI 1.0 snap cards for Power 8 systems. So the framework can be used, I guess, widely in those systems that are available out there. But for the future developments, we want to move beyond CAPI 1. We want to move beyond 10 gigabit Ethernet. And so next slide here shows possibly the card that is beginning to get deployed in a number of test servers, hopefully across a few sites that might be available to the likes of Endric and others. And this card here is the ADM PCIe 9v3. It's based on the Vertex UltraScale Plus VU3P device. This has got the 28 or 32 gig capable transceivers, and therefore is capable of running either 25 gigabit per second on each single link coming out of the QSFPs, or as a full 100 gig link using all 4 lanes in each QSFP. This card also has the advantage that it is not only PCIe Gen 4 capable to an extent, to as much an extent as Vertex UltraScale Plus is Gen 4 capable, and I believe it does work with IBM Power 9 PCIe Gen 4. It's also CAPI 2.0 capable, and it's also got the 25 gigabit per second OpenCAPI link as well. And so therefore this is definitely the next platform we would hope to get this IP ported to, as it certainly will allow a smooth transition up from Snap 1.0 and 10 gigabit per second to Snap, CAPI 2.0 Snap and OpenCAPI Snap, and 25 and hopefully in the future 100 as well gigabit per second links. Beyond this, there's two other boards that this IP could be targeted at. The ADM PCIe 9H7 that we have at our booth, which is a fairly heavy weight VU37P HBM FPGA. This doesn't fit into too many Power 9 systems, but we're certainly keen on seeing them in the Mihawk systems from Wistron. This board is actually multiple OpenCAPI links and is possibly capable of 4, 8 or possibly even 1,200 gigabit per second links, and the HBM may give a good advantage in terms of having a sort of buffer for retry data, if not necessarily for any low latency data requirements of the Ethernet stack. Another board that may be of interest in the future is a low profile card that's very similar but based on the VU33P HBM FPGA, and this has double density QSFP, so it's capable of either taking a standard QSFP 100 gig link or a double density one with 200 gig links on it, and this has got the OpenCAPI link coming out the rear connector, and this should physically fit into a lot more Power 9 servers. And so I'll just hand back to Endric to perform the call for participation. And
so yes, just to conclude, CAPI Snap, very easy to use, allowed us to integrate network protocol processing within a power system within a few weeks, honestly. Most of it was getting access to the hardware and learning about the details of the hardware. What we're now looking for is participation from the ecosystem, people who are interested in driving network protocol acceleration into OpenPOWER and into OpenCAPI, and who are providing us with use cases and applications so we can streamline this acceleration technology towards their needs. Thank you.